AI is everywhere. Hedge funds use it to stress test their portfolios. It proposes pleasing new molecular combinations for perfumers. Linguists use it to translate endangered languages. If you've ever wondered how AI works, you're in the right place. Welcome to the Data and the Story, where we deploy curiosity as our defense and offense in a fast-changing world. I'm CJ Washington. This is the fourth in a series of 5 primers that explores how AI learns. Many Data in the Story episodes, from green energy to extreme weather, will touch on AI. And to better focus on the big picture, I'll send viewers here for the details about how AI works. The first 2 primers covered artificial neural networks and supervised learning. If you haven't seen them and you're new to AI, I suggest you watch them now. They provide the foundation for understanding this primer, which is all about reinforcement learning, put on the map by systems like AlphaGo, the AI that famously defeated Lee Sedol, the reigning Go champion, in a 5-round tournament in 2016. The third primer covered unsupervised learning. You'll want to check it out, but it isn't a prerequisite for today. The 5th and final primer will focus on large language models. Reinforcement learning allows a computer system, often called an agent, to learn through interactions with the environment. As you can imagine, reinforcement learning is a natural fit for training robots. Self-driving cars can maneuver dangerous conditions in simulations. Humanoid robots can practice walking without a single fall in the real world. When it comes to reinforcement learning, you can visualize the environment as a grid. At any given time, the agent exists in a state. You can think of the state as a square. Each state has a set of actions the agent can take. For a simple grid, the actions might be move forward, move backward, move left, or move right. The agent receives rewards for taking particular actions within particular states. If the agent is learning to play Pac-Man, the state is a snapshot of the maze at a given moment. Where is Pac-Man? Where are the ghosts? Where are the pellets? The agent receives a reward, a high score, after eating lots of pellets while avoiding ghosts. The agent isn't told to eat pellets and avoid ghosts. It learns through trial and error, high scores and low scores. The credit assignment problem refers to the challenge of determining which actions led to a reward. The agent might take 100 actions before it receives a high score. It has to learn how to assign credit to each of them. If you're training a robot through reinforcement learning, it's up to you to design a reward system based on the desired behavior. This can be tricky. Telling the robot what you want, but not how to do it, can lead to unintended consequences. Imagine telling your child to clean their room. They tell you it's done. You walk in and the floor is spotless. You open the closet and you get buried in toys. True story. Don't dare look under the bed. In graduate school, I took a course called Machine Learning for Trading. My favorite project was building a stock trading agent trained through reinforcement learning. We used historical stock data and virtual money. The agent's state at any given time consisted of market conditions, the technical indicators of stocks, their moving averages, their volatility, their momentum, etc., the current stock portfolio, and the balance of cash available to the agent. The available actions were buy, assuming it had the cash, sell or hold, assuming it owned the stock. At each state, the agent would estimate the value of each action. Our assignment was to implement a reinforcement learning algorithm called Q-learning, but today we're talking about deep reinforcement learning. In the context of machine learning, deep refers to neural networks with multiple layers. We pass the state information to the neural network. It processes this input just as we discussed in the supervised learning primer. Values are multiplied by weights, summed together with biases, and then passed through an activation function. ReLU outputs a 0 if the input is negative or 0, and passes the output unchanged if it's positive. The output layer assigns preferences to each action. Then, based on those preferences, the agent samples an action and receives a reward. It samples rather than always choosing the highest rated action, so it can occasionally try less preferred actions and discover strategies it didn't already know were good. This is called exploration versus exploitation, a central concept in reinforcement learning. Say the neural network assigns a 20% preference for buying Google, a 50% preference for holding Google, and a 30% preference for selling Google. Half of the time, given the preferences, it will hold Google. But let's say it samples its 20% preference for buying Google and then receives a massive reward. The loss function, through backpropagation and optimization, will update the weight such that it is more likely in the future to recognize the value of buying Google given that particular state. The story of AlphaGo is fascinating, and if you want an exciting description of the face-off with Lisa Dahl, I recommend reading The Maniac by Benjamin Labatut. It's a novel that reads like narrative nonfiction, but I have to warn you, the first two-thirds of the book is about John von Neumann, the legendary mathematician, computer scientist, and physicist, in the entwined creation of computers and nuclear weapons. If you're embarking on the technical journey of AI, you'll certainly find the story of von Neumann told through the eyes of luminaries such as Richard Feynman inspiring. If you're not ready to delve into the math, you might be after reading this book. Keep your curiosity strong, and whatever you're curious about, I hope it leads you back here, and I hope you find what you're looking for. Interested in knowing how LLMs like Claude, ChatGPT, and Gemini work? Subscribe, turn on notifications. It's coming to the data in the story.